Howdy, welcome back to Boolean Maths. We are going to be talking about the arc relationships to chords and circles today. And yes, there is a cat right there. So he's going to be hanging out with us today. All right, let's get to it. Arc and chord theorem. So at this point, you've been studying circles for a really long time. Actually, you know what a radius is, a diameter. You probably know what a chord is, hopefully. And there are other parts that will be discussed, such as tangents and secants. Again, hopefully you know about those from prior lessons, but they will come up again. So as with almost everything in geometry, you have relationships. And so there are distinct relationships within a circle between a chord and its corresponding arc. So the first one, we're going to be talking about theorems here. So, and I'm naming these. Every textbook will either name a theorem or themselves, or they'll just give it a number like theorem 1.2 or something. So this is just my first arc chord theorem that I'm putting in this presentation. It's a congruent, so I'm calling it the congruent arcs imply congruent chords theorem, and vice versa. So if you have a circle and you know that you have two arcs that were created by two chords, if those arcs are congruent or have the same measure, right, the same degree measurement, that means that the chords must be the same. So the theorem reads, in a circle or congruent circles, right? If you have the same radius, it's the same circle, except it's, somewhere else. It's the same exact type of circle. So in a circle or congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So if and only if, let's make that a bigger highlighter. So if and only if, that means that I could read that same statement or that same theorem two different ways, like vice versa, right? So I could start it and say corresponding chords or chords, chords are congruent if and only if their corresponding minor arcs are congruent, something like that. You'd read it, I think you get it, all right, hopefully. All right, so this is a diagram that I just kind of threw here. For fun, though, I thought it'd be nice to jump into Desmos. Desmos not only does graphing calculators, but if you go to the website and you go to the bottom, there's a little geometry link. Not a lot of people know about that. They have a little sketch pad for doing simple geometry. All right, so here we have a circle, and you see two chords there. Now, I don't know if they're congruent or not. One thing that's nice about this program is that we can measure them. So let's quickly measure them. So we can throw some labels on there. Whoops. Let's get that one labeled too. So they are in fact the same, 4.31. And I'm going to move this one around. It's locked. So these two are kind of related. So if I grow the right one, the left one will grow as well, but they are exactly the same. And the reason I'm making it so I can change the size is we want to know if those arcs that correspond are the same. Unfortunately, I can't measure the arcs, but what I can do is I can measure the central angle related to the arc, and that's something that I know you did study. So let's actually, let's draw some segments here. I'm going to put in the radii. And I'm going to color them red. And now I can measure the angle, bam, bam, and then, so you see those central angles. That means that arc DG is 75 degrees and arc BA is also 75 degrees. And in a circle, if you have the same arc measures, then you have the same arc length. So they would have to be congruent in a singular circle like that. Okay, so now if you notice, as I move, either scale the size of the circle, or if I just change the size of the arc, that central angle stays locked. And those are not vertical angles either, so it's not like I'm cheating here. So if you have congruent chords, you have congruent arcs, and if you have congruent arcs, you have congruent chords, and that's what that is demonstrating. Okay, let's do an example. So let's focus on example 1 here. Why don't you pause the video and see if you can do it. Okay, welcome back. So hopefully you recognize that you have arc AB and arc CB have something in common. They both measure 109 degrees. So if they are the same degree measurement, they're also congruent. If they are congruent, the chords that form those arcs must be congruent. So thus, these two expressions are the same. So 5x minus 7 must equal 3x plus 2. We subtract 3x from both sides, we got 7 to both sides. And we got 2x equals 9, and x equals 9 halves, or 4 and a half. So that's the first answer. Take a look at this one. Again, you might want to pause the video and do this one on your own. Welcome back. Okay, again, you have two chords that are congruent. Therefore, the corresponding arcs, this arc and this arc, the yellow arc and the green arc would have to be the same. So therefore we can set those two quantities equal to each other. That means 7x plus 24 equals 115. I'm going to subtract 24 from both sides, and that's going to be 7x equals 91. And then if you divide by 7, 91 divided by 7 is 15. Okay, 7 equals minus. Okay. Moving on. Next arc chord theorem says congruent chords are equidistant to the center theorem, right? That's a fun name. So if you have congruent chords in a circle, that means they both would have to be equidistant to the center. So once again, I have another Desmos example to show you so we can kind of move things around. I believe this is example 2. All right. So this diagram's a little bit better than the one in the presentation. You see we have two chords. And they are equal, and you'll see that in a moment because I'm going to reveal their lengths. And we also have those two red segments. Now notice they're not radii. Okay, they're just distances. So if I start moving this chord around, it doesn't have a label on it yet. I'm sorry, but you'll see that in a moment. You can see that it this is dynamic. I can change the size of the chords, and so yeah. Without further ado, those are we're going to throw some labels on there, and you can see that we have each chord is 5.85 long. Now they're 4 whatever, so you can see I'm growing them, shrinking them, but the chords remain fixed. They're both the same length. And notice the distance from center A to those respective chords. It's fixed at 4. Now it's 4.6. 6.39, and again both chords are the same length. So again, you have two chords in a circle that are the same length. They must be the same distance to the center. In a way, it just sort of makes sense. You'd almost call that a postulate. I mean, you could prove it using congruent triangles easily, but yeah, that's just the deal. So let's look at an example here. So in this example, we have a situation where we have two chords that are in the diagram, and we're not sure if they're equal. They didn't tell us that they're equal, right? There's nothing in the description that says DE equals something with FG. So but let's look at the diagram before we even see what they're asking us, and mark it up. We'll see what we know is equal. What other relationships. So we do know that chord DE and chord FG are both equidistant to the center. And the reason you know they're equidistant is because, and the big giveaway here, and it's super important that you note this, is that not only are the distances here, like these red lines I'm drawing, not only are they congruent segments, but you need those right angles, right? Because that guarantees you that you're taking the shortest path between the center and your line or segment, in this case the chord. But now, since we know for a fact those are distances from the center to the chords, we can now assume that DE and FG are congruent. So I guess I'll use it's kind of hard to label when you have other things going on, like a congruent hash mark. So we're just going to say that the green segments are congruent here. And because the green segments are congruent, that means that DE and FG, those quantities that represent them, are also equivalent. So we can now set up an equation. We have our relationship, and we would solve 32x minus 27 equals 11x plus 15. Go ahead and subtract 11x from both sides and add 27 on it. That's on its own, and we should have 21x equals, so 27 or maybe 32, 42. And then we got 1. x equals 2. I'm plugging this right in, so just verify. So d, our answer is going to be 11 times 2 plus 15, which equals 22 plus 15, which is 37. So, okay, so 22 plus 15, 37. So d equals 37. Now they want us to find the measure of arc MP. They've got a couple things going on here. So why don't you pause the video and try to do this one on your own, and hopefully you'll find success. Okay, I'm assuming you're back now. You will see me do this. Okay, again, they didn't tell me anything about arc and M. They didn't tell me anything about arc and NP or MP, right? But what I do know is that these two chords, this chord and M and NP, they have to be congruent. And the reason they're congruent would be because they are equidistant to the center. And since they're equidistant to the center, that means they are congruent. And if the chords are congruent, then their corresponding arcs are congruent. So this red arc and this red arc are also the same. And since they're the same, those quantities enable us to do this. So anyway, we have our equation. We're going to go 9x minus 43 equals 5x plus 33. Equals 5x plus 33. And the equal, which is this. And I'm going to add 43 to both sides. I'm going to subtract 5x on both sides. And we get 4x equals, and 56. And that's going to be 19, I believe. So now we have x, but they did ask us for arc MP. Okay, so what we need to do is take x, plug it back in, and find out all the arc measures. So 9 times 19 minus 43 is going to be 128. 9 times 19 minus 43. So what that means is that this is 128 degrees, that arc. This arc is also 128 degrees. And the arc we're trying to find is going to be MP. The measure of arc MP is going to equal 360 minus 2 times 128. So 360 minus 2 times 128 is 104. So the measure of arc equals 104 degrees. Okay, that was fun. Next one, perpendicular bisecting diameter theorem. Okay, so it turns out that if you have a diameter that's perpendicular to a chord, automatically you can assume that it's not only perpendicular, but it's also a bisector. So on this diagram, when you look here, you can say, all right, well, look at that diameter DF is perpendicular to the chord. So now I'm allowed to just mark these two chords as congruent. And it turns out also that these arcs that are those little semi-arcs that were created by chord CB, were the arc CB is now cut in half as well by that diameter. So which is kind of helpful. That's kind of an interesting thing. The other thing to note is the next theorem. I'm just going to state it now. The next theorem says that if you look at, well, I take it back. If you look at a segment, or sorry, a chord that you don't know if it's the diameter, and it's a perpendicular bisector of a chord. So if you have a chord that's a perpendicular bisector of another chord, that chord must be a diameter. So you can assume that it's a diameter, and that's like actually a really cool property, which we will talk about shortly. All right, so let's go to the example that's associated with 3. One thing that already jumps out at me is that there should be a degree symbol on that measure of that arc. Okay. So why don't you pause the video, see if you can figure this one out on your own, and then come on back. In the meantime, I'm going to be working on this. All right, so I'm back anyway. So you're back, I'm back. And I'm going to have a sip of coffee. That's right. Okay, so one thing that I would like to do is label the diagram. That's what all good geometers should do. So they're saying the radius is 18. So let's look for a radius that I can label. NE, perfect. NE is 18. You might be questioning, why didn't you label some other radius like NG? I could have, but then I need to use curly braces and stuff. So we know that NG is also that. How about we just go ahead and highlight all the radii? So we can see those. Okay. What else do they tell us? They tell us that NK is 9. Okay, fun fact. Whoops, wrong tool. That's 9. And the measure arc DE is 120. Let's get the highlighter out again. Highlighter, good. Okay, so this arc right here. Again, it's kind of hard to draw curly braces on an arc that's split into multiple arcs, so using a highlighter is a tool for that. All right, so there you go. And then they just want us to find each of these measures. I'm not going to look at them just because I don't even want to know what they're asking. I'm just going to go ahead and take charge. I'm going to label up this diagram as much as I can. It might not be the most efficient way to solve certain problems. You're taking the SATs. You don't want to sit there and just dissect the problem, and have fun labeling everything if you know exactly how to get to your answer. All right. So a couple things. We know that a radius is part of a diameter, right? So if a radius is also perpendicular to a chord, right, being that it's going through the center there, that means I'm automatically allowed to label these as being bisected. Like they're perpendicular bisectors of those chords. Now it's a little bit presumptuous for me to just to say that all of those, that the two chords are the same, because I don't really know that yet, right? I'm not sure. So yeah, I'm not going to even, so if you notice, I gave XK and KY their own congruency marks. They are congruent to each other, but I am fairly confident that XY and DE, those chords, are the same, but we're not sure yet. Okay, but one thing I do have the ability to do now is I have the ability to solve for different parts of this triangle right here. I just highlighted that in red. And the reason I can do that is, since this big red arc here that I've already highlighted, but I will just add more red to it, since we know that that's 120, right? It gets cut into two equal parts. So now I can actually go ahead and unhighlight it and just write 60 and 60. Because if a diameter or radius is perpendicular to a chord, then not only does it cut the chord in half, but it also cuts its associated arc in half. So, and since that arc is 60 degrees, we know that the central angle associated with said arc is also 60 degrees. And so we have a little mini right triangle there. The radius is the hypotenuse. And not only is it a right triangle, it's a 30, 60, 90. So if you recall, the side that's across from a 30-degree angle is the short leg, right? So the short leg is always half the hypotenuse. So you don't even need to use trig. You can just label that 9. And if that's 9, this little piece here, I don't think they asked for it, but it's 9 root 3. Maybe they did. I don't know. That's 9 root 3. Okay. And if that's 9 root 3, this is 9 root 3. Now we also know that I can come back over here and I can eliminate that other congruency mark. And I know that all these segments are the same because since NH and NK are the distances to those chords, I'm technically allowed to, now I don't even have to assume, I know that KY and DE are congruent because they're equidistant to the center. Okay, so there you go. And now what were they asking us over here? They said, what's the measure of arc GE? All right, we have it. It's let's do this in blue. It'll just be more fun. Arc GE is 60 degrees. What's the measure of angle HNE? Also 60 degrees. It's kind of a guiding question here. Angle HEN, 30 degrees. Yeah, they're really trying to lead us towards that 30, 60, 90 scenario. And then HN. HN is just 9. So yeah, we actually went above and beyond on this one. This problem would have been a lot more fun, in my opinion, if they were like, what's XK? Because then you would have been like, ooh, I don't even have any connection to that. But then once we established those other relationships, you would have been like, I know it. All right, so this video is definitely running kind of long, so I need to wrap this up for you. But lastly, we talked about being able to determine if something's a diameter, given a perpendicular. Well, given that a chord is perpendicular to another chord, if one chord is perpendicular to another chord, then it would have to be, or a perpendicular bisector of another chord, then it has to be a diameter. So this last example is an interesting application of that. Say you have a big circular piece of wood, right? And you want to make a table out of it. You want to put an umbrella stand through the middle, and you need to locate that center because it's not necessarily easy to locate a center. It depends on how the wood was created, but let's just assume it's a perfect circle. So one way to locate the center of a circle, if you don't know its center, is to just draw a couple chords and do some perpendicular bisectors. So I believe in Desmos, I should have an example for here. And I do not, so I'm going to just start a new construction, and I'd like to demonstrate this to you. So here we have a circle, okay? And then in the circle, I'm going to go ahead right now, and I'm going to eliminate, I'm going to hide the center, okay? So by hiding that center, I would like to locate it, and then we'll reveal the center in a moment. So let's draw some chords. Here's a chord. Here's another chord. They're both very different chords. And then what I'm going to do is I'm going to use some of these tools. I'm going to construct a perpendicular bisector. So the perpendicular bisector is going to go through the midpoint of that segment, and I need a midpoint of this segment. And then of course I need perpendicular lines. So I'm going to put a perpendicular line here and a perpendicular line there. So I just constructed the perpendicular bisectors. Let's color those perpendicular bisectors red so you can really see them. And then we can put a point right at their intersection. So you're probably wondering, like, you really just jumped into this. Like, why are you finding the perpendicular bisectors of those chords? Well, a perpendicular bisector of a chord is a diameter, and one diameter is not going to do the job. It's only going to serve to show me a diameter, but if I have two different diameters where they intersect, will of course be at the center, okay? So, and I could slide these pieces around, and notice the chords don't have to be the same length at all. They're going to still always go through that center. So see how I keep changing this chord. And let's reveal the hidden center that I hid at the beginning. So there it is. If you want to give these some names. There was center A, and then now I have center I. So I'm hiding A, bringing it back. You can see it's perfect. So there you go. You should try it yourself. It's fun. All right. Well, thanks for watching, and hopefully that was helpful.